to the organizers. Well, especially I talked to Alexia, but also with Raya. And it's my first QEI conference, but I'm impressed how big the idea has become and the private companies involved and so on. So, well, today my talk is about information flows, which is a tool to interpret nanomachines as Maxwell demons or as information motors. So it's trying to see if we can detect some kind of information processing in nanomachines. What I understand by a nanomachine is machines that work first autonomously, so there is no driven mouse. Ah. Okay. So I have. So yeah, for me, nanomachines are systems, microscopic systems. So well, the main thing is that they are in a noisy environment, so they have fluctuations, and they work in a steady state, in an autonomous way, and they do things. I mean, they can be energy transducers or motors or thermal engines or refrigerators and so on. And the idea is to use these information flows to interpret these machines as Maxwell demons. And this is the main idea of the talk. The whole talk is classical. I told Alexia, well, Alexia wanted me to talk about thermodynamics of information, and I said, but all my work is classical. And still, she asked me to come. So, but I think in this topic it's okay. It's nice to develop. I mean, the classical intuition is I think is very helpful to address quantum problems. There will be a final reference on quantum information flows, which are also studied, but my talk is going to be classical. And also it's going to be very pedagogical. I don't know, but for some people, maybe some of the things that will be very, very trivial or well known. But this is also what Alexia asked me to do, something kind of pedagogical, self-contained. So I will start, I will start with very basic things on the Maxwell demon. It's one version of the Maxwell demon, which is the Ciliar engine, which probably most of you know. But anyway, I will review what is the Ciliar engine, and then very basic concepts of information theory, like Shannon entropy and mutual information. And then we will go to the information flow, which is not trivial at all. So, and the talk is a bit, a summary of this paper that you can find in this book. This book is the proceedings of a conference that Xavier Boujou and Christian Joachim organized in Toulouse about nanomachines. These people is very, very funny. They organize a race of nanomotors, which you can see in YouTube. You can watch in YouTube, and it's very nice. And this is also a kind of self-contained paper done in collaboration with Jorge Tabanera, was my PhD student at that time, and Natalia Ares, who will be here tomorrow, I hope so, and Federico Fedele, and also some people from Natalia's group is here. And the notion of information flows goes back to 2009, although the paper who really applied this to machines was this paper by Jordan Horowitz and Massimiliano Esposito. So let me start with the Ciliar engine. Well, Maxwell demon, I guess everybody knows what is a Maxwell demon. Maxwell demon is an idea that Maxwell had in the 19th century to show that if somebody has information about the microstate of a system, or more precisely about fluctuations of a system, then this person can extract energy from a single thermal bath, or it can defeat the second law. So this was the idea. And in 1912, Leo Szilard introduced a kind of very simplified version of the Ciliar, of the Maxwell demon. But the idea is the same. It's an external agent who manipulates a system and extracts, measures something in the system So acquire some information about the microstate of the system, and according to this information, operates and can defeat the second law of thermodynamics. And this is the idea. It's a single. It's a molecule. It's a single molecule gas in a box. The box is in contact with a reservoir at temperature T. You can imagine this as if the molecule, every time it collides with the walls, it gets out with a thermal state, thermal velocity, let's say, Maxwellian velocity. The idea is to let the molecule evolve here, and then insert a piston which partitions the box into halves. And then if you measure in which half is the particle, you can make an expansion, like the expansion of a gas. In this case, it's a single particle gas. And then you go back to the initial state. And in this process, it's a cyclic process. You have a contact with a thermal bath because of the walls, and there is also an external agent that moves the piston, insert the piston, and so on. So there is a work and a heat, like in the typical engines in thermodynamics. And you can calculate the work. To calculate the work, we use just this PdV as in undergraduate thermodynamics. And it's this quantity, the log of the ratio between the final and the initial volume, which is 2. So we have kT log 2. So we can extract energy from a single thermal bath in a cyclic way. And this is, we are defeating the second law of thermodynamics. The second law of thermodynamics, one of the formulations or the statements of the second law, the Kelvin-Planck statement says that it is impossible to extract energy from a single thermal bath in a cycle. So this is what we can do here. In my talk, I will use the convention for the work and heat in stochastic thermodynamics, which is everything that enters into the system is positive. So the work W will be minus the work that we extract. Anyway, you can extract work from here. So there is a problem. For 1 century, people thought there is a cost, an energy cost in the measurement. Then Bennett and Landauer came with the Landauer principle, and they say, no, there is a cost in resetting the demon's memory and so on. But before going into this, the Steeler engine allows one to study, to analyze this in a quantitative way, because the information you acquire here is very easy. It's a yes/no experiment, yes/no measurement, and the work that you extract is also easy to calculate. It's kT log 2. So this Steeler engine allowed us, the people working in thermodynamics of information, to really quantify how much information you acquire from a system, how much work you can extract for a given information. And this is, for that we need concepts of information theory, and this is the thing that I'm going to talk about. I will introduce one of the main concepts in information theory, and then I will use this to analyze the Steeler engine later on. So you have probably heard about the Shannon formula, the Shannon entropy. Some people call it Shannon information. This is not true. It's information. We will see that information is more related with another concept of information theory, which is mutual information. Shannon entropy is a measure of the ignorance that we have about a random variable or the uncertainty. So this is the Shannon entropy is the famous rho log rho. And you can have different, you can measure in different units. Sorry, if you put here log of 2, then you have bits. If you put natural logs, you have nuts. And if you multiply by the Boltzmann constant, you can have this also in units of joules per Kelvin, so in units of entropy. Okay? For instance, in bits, the Shannon entropy of a random variable is the number of bits that you need, zeros and ones, that you need to determine the random variable. But this is not really information. This is ignorance. So what is information? Information is information is the reduction of my ignorance about something. So let me illustrate, and this concept is this is, okay, information is how my ignorance is reduced when I get some information about the system, via some experiment or via some question, for instance. So suppose suppose that you play the typical game of thinking of a number or thinking of a character and so on, and then she asks, this is a normal one, or but is a presenter, or?
No, but it's fine.
This is a mouse. It's too slow. Well, okay, so I think of a number, and then you ask me a question. You have to guess the number. So you ask me questions about the number or a character. You can, for instance, I can think of a historical character, and you can ask, it's a woman or it's a man, and so on. And then my answer is Y, and the information is how the answer Y reduces the ignorance of X. So this is the ignorance. Oh my God, this is too slow. This is my ignorance or uncertainty before the question, and this is after the question. And how this is reduced is the mutual information. So if you put the formulas, P log P, and for here, P log P, but conditional to the answer, and then you average over the answers, this is the result. And you can group the terms in this formula, and you see, first you see something which is not, it's not completely, oh my God, I have problems with the, you first see something which is not completely expected at the beginning, that is symmetric under the change of X and Y. So Y provides the same information of X, or Y provides the same information about X as X provides information about Y, which is not something that a priori I would say. So this is the mutual information. It's symmetric, and you can also identify here the entropy. Sorry, this P log P is the entropy of X and Y together, and you can write the mutual information at this entropy of the total system with a signal with minus Sx, Sy minus Sxy. So this is also a very important mutual information in the thermodynamic of information plays two important roles. One is the reduction of ignorance, and the other one is given by this formula. Is better here. It allows you, the mutual information allows you to write the entropy of a compound system in terms of the entropies of the individual systems minus the mutual information. So this is also very important. Okay, in stochastic thermodynamics, if I have to summarize in one word what is one of the most important results of stochastic thermodynamics, is this one, is to prove that Shannon entropy obeys a second law of thermodynamics. So this is not easy, that if you sum the change in Shannon entropy of a system plus the entropy in the environment given by the Clausius formula, Q divided by T and so on, this is bigger than zero in any process. This is, to prove this, you have to go to master equations, to Hamilton equations. The proof is not completely, you need hypotheses on the initial conditions and so on, but you can, the message is that you can use Shannon entropy as if it were thermodynamic entropy, and you have a second law like that. If your system is in contact with a thermal bath at a given temperature, with a single thermal bath, and you are interested in energetics rather than in entropy, it's better to use free energy. Free energy, remember, is E minus Ts, and the second law in terms of free energy is given by this inequality. The work that you need to do to go from one state to another state is always bigger than delta F. This means that in a cycle, delta F is 0, and the work is always positive. You can never extract work from a single thermal bath. Okay. So let's analyze, and if we can use the mutual information, we can use the mutual information here to write the entropy of a compound system in terms of the individual entropies, and also to write the free energy of a compound system in terms of the free energies of each individual system. So I will use the second one, the free energy as decomposed into the free energy of X, the free energy of Y, and the mutual information to analyze the stellar engine. Now we have two systems. One is X, the particle, and Y is the demon. So the demon we are taking into account, which is one of the strategies to, let's say, resolve the Maxwell-Demon paradox, is to take into account the physical nature of the demon. So the demon is a physical system, which will have some states. We are only interested on the outcomes of the measurement in the demon. So we are going to consider that the demon is initially in a state given by Y, and the particle is in a state given by X. So the free energy, they are uncorrelated, or they're independent from each other. So the free energy is Fx plus Fy. Then the demon measures where the particle is, and it becomes correlated with the particle. So now there is the mutual information. The demon has information about the particle, and this is given by the mutual information between X and Y prime. Y prime is the new state of the demon because the demon updates its state. And finally, the demon performs the expansion, and the correlation is lost. So at the end of the process, it's a cycle, so X, the gas, goes back to the same state, and the demon, we assume that the demon performs this operation without changing its state. So now let's apply the second law. The second law tells you that the work you need, the minimal work you need to perform each of these operations is always bigger than delta F. The difference between the free energy after minus the free energy before. So if you subtract this free energy from that free energy, you get Fx cancel, and then you get delta Fy, which is Fy prime minus Fy, plus T, and the mutual information. Then here is the most important step, is the feedback. What is the minimal work to do the feedback? Is delta F. If you subtract this from that, you get minus Ty. So now the work is negative, so you can extract work. Remember, minus W is the work you extract. So you can extract KT log 2, which is what Szilard told us 1 century ago. But now, to have a real cycle, you need to restore the demon state. We say sometimes restore the demon's memory. So we have to go from Y prime to Y. And in doing so, we have also to do some work. And this work is the work to restore is minus delta Fy. The total work, of course, is 0. the minimal work is 0. So we are not extracting energy from the thermal bath. Apparently, we extract energy from the thermal bath here in the feedback, but we pay a price either in the measurement or in the restore of the memory. The famous solution by Charles Bennett was to conceive a memory or to devise a memory where the work to measure is 0, and there was a work needed to erase the memory, which was KT log 2, according to Landauer's principle. Don't be confused with Landauer's principle. Landauer's principle tells you that there is that eraser, certain type of erasure needs work, not all of them. For instance, you can have also examples where this is 0, the work to erase the memory is 0, and this is positive. In any case, if you sum the 3 works, you will get 0. Okay, but now look at this, process, looking at the mutual information. You see, here the daemon measures, and what the daemon is doing is increasing the mutual information between the daemon and the system. This is measuring. Measuring is correlating the daemon and the system. And feedback is exploiting these correlations, in this case Y, to extract work. Okay? So this is the general idea. If we now go from free energy to entropy, free energy is very nice when you have a single thermal bath. But if you have more complicated environments, it's much easier to think of entropy. So the entropy of a compound system is this one. The entropy of system X, system Y, and the mutual information. And now suppose you have a general machine, not step by step like in the Ciller engine. You have some machine that works with continuous time. Now compute the mutual information between X and Y. So you have 2 systems. One is candidate to be a daemon. We will see that in machines, sometimes the daemon, sometimes it's not obvious who is the daemon and who is the system. So you have 2 systems, and you have a mutual information between the 2 that can have, for instance, this behavior. So according to our last slide, when the mutual information increases, we can identify this as a measurement. And when the mutual information decreases, this means that in the case before, the free energy decreases. You can exploit these correlations to extract work or to do useful things. Okay? So this is the idea that Horowitz and Esposito apply here in this paper. But there is a problem that this is nice to analyze the Ciller engine or engines where there is a driving. So you have the behavior of the system changes in time. But now suppose you have an autonomous machine. An autonomous machine can be, for instance, machines that are in biological cells that consume ATP and they rotate to move some flagella or something like that. It can be a heat ion pump in the cell as well, or in some devices, in some nano devices, electron pump. And these systems reach a steady state. So you have a stationary state. Of course, there are things happening because the steady state is non-equilibrium. So in the case of a flagella, you have rotation. But technically, this is a steady state. And the problem with the steady states is that everything is independent of time. All the averages, are independent of time. Of course, trajectories are dependent on time, but averages are time independent. And these entropies are averages. So all these quantities, if I take my formula that the entropy is the sum of the individual entropies minus the mutual information, and I make a time derivative, this is the dot here, this is constant. So I cannot identify a moment of measurement and a moment of erasure. So this is the problem if I want to apply these ideas to machines, autonomous machines in steady states. So what Jordan Horowitz and Massimiliano Esposito thought? Well, this was actually, this was before by Armand Alevarjan and these people. They introduced the information flow, which is the following. You take the mutual information and you calculate its derivative, but moving only system X. So you freeze Y, you move X, and you calculate how the correlation, the mutual information is changing. And the same for Y. You see? This is super slow. So you see T prime, you make the derivative with respect to T prime, and T prime is only in Y. So you are freezing X. Okay? This is, if you calculate the total derivative of the mutual information, then this is the sum. This is not always true, although it looks like kind of a chain rule. This is not always true. I mean, you need extra condition, which is that the system must be bipartite, but this is a technicality. So in the steady state, you have that this information flow is minus the information flow in X, but they are not zero. The total derivative is zero. So the mutual information is constant. But if I freeze X, I get a variation in the mutual information, and if I freeze Y, I get also a variation of mutual information. So now the idea is the following, that, for instance, suppose one is positive and the other is negative. Suppose that this is positive. This means that the motion of Y, the evolution of Y, is increasing the correlation between the two. So Y is measuring on X. So Y is the demon. So this is a kind of a trick. You calculate this, you see which of the two is positive, and the one which is positive is the demon. It's a kind of signature or a way of detecting which is the demon. Yeah. Okay, but this is nice, a kind of recipe to see in a bipartite system who is the demon and who is the system. But there is something more, which is a second law. There is a second law for these bipartite systems. For this, I need to introduce the environment. Suppose that you have two systems, and each one is connected to a different environment. In the case of the Steeler engine, the motor, the engine, and the demon, we suppose that they were in contact with the same bath. But you can imagine, of course, if we need, if we want non-equilibrium steady states, we need different baths, different temperatures, different chemical potentials, and so on and so on. So consider that you have two environments, an environment for Y and an environment for X. The nice thing is that you can have two second laws for each of these quantities. Let me explain why this is a second law, because maybe the way I'm writing this, you are familiar to this, no? The second law is that the entropy is positive. Well, this is how the second law is locally modified because of this information flow. So usually you have this second law, the entropy is positive, and the entropy is positive, but the information flow allows you to transfer entropy from one system to the other. More or less, this is the idea. Okay, this is not a proof, but it is an idea of how we interpret these two equations. So remember that we have this formula. This was the formula that I used in the first slide, almost in the first slides about mutual information. It's the definition of mutual information and then a time derivative. And now we have the information flows here. So the standard second law, what it's telling us in stochastic thermodynamics, it's telling us that the entropy of the universe increases, which is the entropy of the system and the entropy of the environment, okay? So this is the standard second law. Now, if you use the mutual information, you can write the total entropy as the individual entropies minus the mutual information, which can be also split into a contribution of X and a contribution of Y, and you have this expression. And now you can identify here 3 terms that only affect system X, and 3 terms that affect system Y. And then it turns out you need to go to the Hamiltonian equations or the master equation. It turns out that each part obeys the second law. And now, if you are in the steady state, this is 0, and this is plus IY. So I have the 2 second laws. So this is transparency just to show you what is the origin of these 2 second laws. Of course, when you sum both, this plus that, the information flow vanishes, and then you get the standard second law. The nice result here in information flows is that you have local second laws for each of the systems. So now let's put all these pieces together. So we have 2 systems with environments, and to fix ideas, I will assume that the information flow is positive for Y, which means that Y is the demon. Y is measuring on X. We have the 2 second laws, and IY is positive. And this is the nice thing. If this is positive, I can reduce the entropy of this environment. No? Because this is bigger than 0. So this is positive. This can be negative. So I can use this to pump heat from a cold reservoir to a hot reservoir, or pump electrons against the field, and some useful things. But I have to pay a price. What is the price? The price is in the demon. It's exactly as in Szilard a bit, no? Szilard can reduce the entropy of the environment, the demon, but to measure, now this is positive, I need to increase the entropy of environment Y. So the entropy becomes a kind of resource. I have Y is using resources from its environment to measure on Y, and then the whole machine is able to reduce the entropy of the environment in Y. This is the picture. You have questions? Please, you can ask. Because this is probably the key thing in my talk. You can even, these positive quantities, this quantity and this quantity, you can think of them as an entropy production in each system. An entropy production in each system. And this entropy production must be positive in the 2. In this paper, we introduced something which is a bit silly, but I like it, which is engineers love this type of diagrams. They are called Sankey's diagrams. They are diagrams where you can represent graphically the leaks in some resource. Here, the resource, as I said before, the resource here is the increase of entropy in the environment. If you go to this equation, and you see that the entropy, the increase of entropy in the environment is equal to the production of entropy plus the mutual information, which is represented by this diagram. In this diagram, the width of each part of the diagram is the corresponding quantity. So this is the increase of entropy in the environment Y, and it's split into two. One is the production, and the other is the information flow, which is also split into two. One is the entropy production in X, and the decrease of entropy in X. So it's like you have a resource, which is this one. You have leaks, which is the production of entropy. It's irreversible, so it's something that, and you have the information flow, which is a kind of transfer of this resource, this entropy production, from system X to system Y.
If I can ask a quick question, can you say again the assumptions in which this is valid, or is it always true that?
This is always valid. The only assumption is here, I mean, it's not an assumption, it's just to fix one of the two. I mean,
so
the diagram is valid for IY positive. So when Y is the demon.
But so is it always true that information flow can be interpreted as an actual entropy? A thermodynamic entropy.
This is a definition. If I mean, you take the definition, and you can compute this. Well, no, sorry. There is an extra assumption, which is the system must be bipartite. What means bipartite? In discrete system means that you cannot have simultaneous jumps of X and Y. In continuous systems means that the Langevin equation for X and Y, the noises must be uncorrelated. So this is the otherwise, this formula is not true. This formula is not true. There are people, I think Gonzalo is also and Jose are working on information flows in non-bipartite systems. No? You do. You have a poster on that or no? Okay. You can ask them. Okay, so final 10 minutes. We applied this to the nice experiments that Natalia is doing and his group and her group are doing in Oxford. Natalia probably will tell us tomorrow more about these experiments. And people from the group is here as well. And the experiment, I have this. So the experiment, so I can get rid of this stupid arrow. You see the pointer is not very, you see the pointer? Okay. So, well, in Natalia's lab, they have a nanotube connected to some electrodes. And then they, with some gate voltages, they managed to create here quantum dots. Sometimes one quantum dot, sometimes two, sometimes we don't know how many. But essentially, the system is a nanotube, which is a kind of a string. It's an oscillator. It's a harmonic oscillator. Although we have also studied anharmonicities, but let's think that this is harmonic oscillator, and a quantum dot, whose energy epsilon depends on the height. I mean, on the motion of the nanotube. So you have 2 degrees of freedom, two degrees of freedom which are coupled. No, one is the occupation number of the dot, and the other is the amplitude of the oscillation. Gerald was also in the group, visiting the group, and yeah. So this is what we have. So we have 2 systems. One is the oscillator, let's say, the amplitude of the oscillator. We think of a one mode oscillator. Of course, you can have different, I mean, the oscillation of the nanotube is a whole string. So, but let's think of the amplitude of the fundamental mode. So you have an oscillator. It has a lot of inertia, so you have to consider position and velocity. And then you have the occupation, which is this Y. So you have two systems coupled. Eventually, the idea is to, and in some experiments, some of the transport is coherent. In the experiments that we were discussing, transport was decoherent, and the motion was classical. So everything is classical here. Although Natalia's goal is to do, and she's doing some quantum experiments here, but my analysis is going to be classical. So here we have these two, and the electrons are, here is the Fermi, in the Fermi Cs in the electrode, and this red thing are the barriers, which play also an important role. So you can do all the math. It's it's very simple. I mean, this is a Newton's equation for a harmonic oscillator with some dissipation here. And here is the fact that if the quantum dot is occupied, so P is 0, 1, depending on if it is occupied or not, you have some equations. You have a master equation for the population, so you can put everything together in a single Fokker-Plumb master equation, which is an equation for the probability density of position, velocity, occupation number. So you can solve this, I mean, not analytically, but numerically, and you can calculate the mutual information and everything. So I will finish with two interpretations. Of course, the system has a lot of different regimes, self-oscillations, pumps, etc. But I will show you two possible scenarios where the information Maxwell-Demon interpretation makes sense, which is, the first one is an electron pump. Here, by the way, you have a thermal bath, which is responsible for the dissipation of the oscillations. The oscillations, if you let the system evolve, the oscillation decay. So there is a dissipation, maybe because of the elastic dissipation in the tube, maybe because of some friction, although it's a vacuum, so we don't know. We don't know the dissipation mechanisms, but there is a dissipation mechanism. So you have a temperature, you have a bath that affects the oscillator, and then you have the electrodes. This is much easier to control, and they have a temperature and they have a chemical potential. So, for instance, you can have what we call chemical work, which is essentially electrical power. So, if you pump electrons against the chemical, against the field, this is positive. So here you can have, I will show you two, or maybe just one, because you are who's my chair? He's busy. So I will show you this one. Here the system is the X and Y, is the dot and the oscillator. But you have connection with two bats. What is doing the electron pump? The electron pump is pumping electrons against a gradient of chemical potential or of potential, against the field. So you have a power plant, let's say, an electron pump. And where this energy comes from it's a thermal machine. It's taking energy from the hot bath, it's releasing energy to the cold bath, and it's pumping electrons. So the regime in this system, there are a lot of different, although the equations are easy, here you have one of the main things is these barriers. Because they control the rate of motion from the electrode to the quantum dot. Okay? So this is how the electron pump works. The barriers, this is the width of this red part is the width of the barrier. So the narrower the barrier, the better, I mean, the easier is for the electron to tunnel, okay? So, and now we have, this is the dot, which you can also imagine is changes because the nanotube is oscillating, okay? Here, who is the demon? Well, the demon is the nanotube. Why? How can we interpret this? Well, if you put this scenario in your system, you can pump electrons from against the field. Why? Well, this is the explanation. The explanation is that when the dot is empty, the nanotube equilibrium position is this one. When the dot is occupied, the gate voltage exerts an attraction and it goes down, okay? So this is the idea. Empty, occupied, empty, occupied. So somehow the nanotube is feeling if the dot is empty or not. It's measuring, and it's true. When this is empty, is here, now suppose that some electron jumps, now the dot goes down, and what happens? If we fabricate the barriers in such a way that the right barrier is narrower here than the left, and when the nanotube is down, the right barrier is wider than the left barrier, what happens is the following. If it is empty, this is the narrower barrier. So it's like if the demon is open, this path. But when the demon detects that the electron is here, it goes down and close this barrier and open this one. I don't know if you can follow it. But, okay, so, and with this interpretation, of course, is in agreement with the information flow. You calculate the information flow, and which one is positive? The nanotube. And then you can write whole Sankey diagram, one of these diagrams for this, and calculate when the efficiency is bigger and smaller and so on. But the design of this, we could, I mean, I would say that it was the opposite. We came with this scenario, and then because of the information flow, we could interpret this as a demon opening and closing barriers. Okay. There is another example which is nice because it's the same system, but changing the parameters, especially changing the barriers. You can make a heat pump where the demon now is the dot. The demon now is the dot. And it is in agreement with the sign of the information flow. But I don't have so much time here. Why is the demon the dot? Sorry, the dot, yeah, because what it is happening here, the nanotube is a harmonic oscillator. So you have two parabolic potentials. And what is happening is that here, by occupying or leaving empty the dot, you are changing between two potentials. And it turns out that the dot detects when the oscillator is up and then switches to the other potential and so on. So here, the correct interpretation is that the dot feels if the system is up or is down and operates and changes the potential accordingly. This is surprising. Okay, this is like my first slide. My first slide was, the mutual information is the reduction of ignorance, but it is symmetric. So X provides information about Y provides information about X. And in physical systems, it's a bit the same. But in some regimes, it's the motion of y. Remember what is the information flow? I freeze x, and I let y. So if I freeze x, I freeze the dot, and I leave the nanotube to move. In this case, no, in the other case, the mutual information increases. So the demon is the nanotube. Here, if I freeze the nanotube, and I let the electrons occupy the dot, then the information increases. So now the demon is the dot. Okay, so that's the conclusion is, okay, we have these second laws, but the second laws are not good news because actually we have the second law, is single inequality, and here we have two, which actually if you sum the two, you get the second law. So it's an extra restriction. So for our engineers, this is not good news. You have an extra restriction to the machines that you can do. Well, I've shown you the information flow concept and the application, but the question is, well, it's nice, no? Because you can talk about demons and so on, but is this really useful? I mean, well, for us it was kind of useful because, I mean, of course, whenever you have a new picture of something, even though the mathematics is the same, but you have now an intuitive picture of demons and information, it helps you to design things and sometimes to optimize things. In the paper that I've shown you at the beginning, I think this is not explicitly said, but it is there. There is a paper here by David Sivak and Yannick Eric. They are in Canada, in Fraser University, and they have done a lot of work on information flows. And here they claim that information flows are really useful to optimize the performance or the efficiency of motors. And finally, I promised you to say this has been extended to quantum systems. This is one of the first papers, but there are more. I think Gonzalo and Jose are also working on that, no? Or no, it's classical. But there are more people doing information flows for quantum thermodynamics. So yeah, that's it. Thank you very much. And as I said, most of the content of the talk is in this paper with Jorge Tabanera, Federico Fedele, and Natalia Harris. Thank you.
All right. I really hope there's not many
temperature.
Sorry?
We always consider thermal reservoir with a given temperature.
Yeah.
And is it could we go, because for instance, under erasure, assume a temperature exists in the reservoir, in the environment. Do we know if, for instance, there is a limit to erase a memory in the absence of thermal assumption, or is it something we know?
Well, there's I guess you're talking about non-equilibrium baths, no? And finite reservoirs.
So the thing is, so I come from the quantum background, and for instance, if you assume a thermal environment, it means that the statistic of your environment follow a very specific distribution. But it's just it just happens that it's often the case, but it's very specific actually.
Yeah, in quantum thermodynamics, you can imagine ancilas which are just 1 qubit and things like that. The things that have been studied more are non-equilibrium thermal baths, like squeeze baths, for instance. Gonzalo has a lot of, or some papers on that. So you assume that your environment is not in a thermal state. Or the second thing is finite reservoirs. So it's a thermal state at the beginning, but it's finite. And then it is. These are the two cases, and I think there are a lot of papers. No, Gonzalo probably knows more on Landauer's principle here, there, and so on.
So maybe I will rephrase my question differently. Are we sure that we necessarily have a non-zero cost to erase a memory? Because usually we assume thermal reservoir, maybe do generalization, but there is still specific assumption about the system. So are we 100%, is it rigorously proven that necessarily there is a positive cost to erase a memory if we relax the thermal assumption?
Well, I must say that you can erase without cost, even with thermal reservoirs. Landauer's principle, some people, the problem with Landauer's principle is that it's so nice to see, eraser means, implies heat dissipation. But it's not true. It depends on how is the memory, and it depends on what is the procedure to erase. For instance, if you take a easy model, which is in up or down, and you decrease the coupling between the spins to 0, this doesn't dissipate any heat, and the information is erased. So it is.
Okay, so you can erase with 0 energy.
You can erase with 0 energy, of course, yeah. The Landauer principle applies to a very specific, which should be called not eraser, should be called, I have this crusade. It should call overwriting, because Landauer's is something that is a memory which can mean 0, 1, and you overwrite, you put a 0. Actually, he called it restore to 0. You can think of this as eraser, but it is a specific procedure, process of erase.
Thanks for the talk. So my question is that you have defined the second law here as a entropy production rate. But does that also, I mean, have you also assumed that this is for the memoryless environment? Because with non-Markovian environment, we can always sometimes see that the entropy production rate can be negative, whereas total entropy production is always positive. So is this assumed here?
This is these are normal reservoirs, and assuming that the entropy production is positive. So you mean in non-Markovian systems,
the rate can be
you can
negative
have
sometimes.
no. This is actually in classical. I think this feature of the negative entropy production is I think is quantum.
Yes,
I
mean,
think
okay, I am
the classical. Even in non-Markovian classical.
okay.
Although non-Markovian classical, you have to really be careful.
Yes, yes.
Because you need to obey fluctuation dissipation and so on, but you don't have this.
Okay, I have a quick question. Thank you for the talk. And my question to you, in the experiments with the nanotube, what is classical and what is quantum there?
No, okay. The experiment, Sophia also knows more than me on that, probably. The experiment is well, the experiment is the experiment. It's
what is
whatever
treated
you
as
have.
quantum?
But you can, the experiment can be quantum if the transport is coherent. And also it can be quantum if the oscillator, if the temperature is so, here is millikelvin, but still the motion of the nanotube is classical. So how can you have quantum? You can have quantum transport.
Yeah, if we have coherent interaction, we can have quantum
Yeah,
transport.
but in my analysis, because it's this master equation here, this is classical. Whenever you have that the state of the dot is 0, 1, and you have a master equation, it is classical.
Thank you very much.
But the experiment can be quantum, and eventually it could.
Too many questions.
Just when, is that working? Yeah. So in terms of applications, the one place where charge transfer and mechanical motion are strongly coupled is in biophysics of membranes and ion channels in membranes. Are you aware of anybody who has applied these techniques to look at optimal those?
For instance, this actually, all these nanomachines are more. I mean, the inspiration has been molecular motors in the cell. For instance, this paper is okay. They are models. This paper is a model with the states and so on. what we call kinetic models. No? You have several states, and you can have jumps, obeying detailed balance, and so on. So, and you have consumption of ATP, and rotation against some torque, or something like that. So this is a case, and yeah. No, and there are plenty of attempts of application.
So you didn't let me ask my question, but we have the coffee break now, so I'll ask them personally. There's a small announcement.
Thank you.
Yes, so, well, let's thank Juan again.